Hey guys, hello everyone and welcome to the channel. So in this particular video we are going to understand Bailer and Ray-Dutt twist. Now this video is going to be a little different from what I used to post over here. In this video I will try to explain you this topic in a more interactive way, alright? And at the end of this video I'll also discuss some of the questions which can be asked from this topic. So I just have these tiny models of molecules, alright? So I'll just try to explain you about the Bailer and Ray-Dutt twist using these models. All right. So without wasting much time, let's get into the video. Alright, so the idea for this Ray-Dutt and Bailer twist was pretty simple, okay? It was seen that if you have a particular molecule, which is, let's say, a octahedral molecule, and if it has chelating ligands around it, it has bidentate ligands, which is going to form something like this, okay? If you have the molecule something like this. Now you can see these bonds are showing the chelating ligands, okay, which are joining the groups like this. So this particular octahedral molecule can show its it can form its enantiomer through twisting. So you don't have to break or form any bond, it can just do that with the help of twisting, okay? So that's the main idea of this Ray-Dutt and Bailer twist is. I'll show you in the further clips that how this twisting happens, but what the idea is to just to form the enantiomer of this particular species into it. So this was, first of all, this was observed by Ray-Dutt, and then Bailer also did it using some other phase of the octahedral molecule. We'll try to understand this in more detail in the further clips, all right? So the basic idea is this only, that you have to convert one of the enantiomer into the other. So if one is the R form of this, so you have to convert that R form into the mirror image of it using this particular twisting of the bonds, okay? So let's see that how actually it is being carried forward. Alright, so I will start from this particular model of the octahedral molecule. You might have seen the octahedral molecule in this way, where you have the metal at the center over here, and you have 1, 2, 3, 4 ligands surrounding this metal on the equatorial plane, this one top axial and this bottom axial ligand. So you have 6 ligands surrounding this particular metal, and it's quite it's moving a little bit, but yeah, that's how the octahedral structure is, what you are more familiar with, right? That 4 ligands surrounding the metal on the equatorial plane and 2 ligands on the axial plane. This is what you have already seen. Now what structure I have shown you, this particular structure basically is the cluster kind of structure of this octahedral molecule, right? So here I am not showing the metal in such, right? So what I have shown over here are just 6 ligands. All right, so let's keep it aside and let's look upon this particular structure. So here if you see, the metal is present at the center over here somewhere, right? All the 6 ligands are surrounding the metal as such, like this. Now this is how the octahedral molecule looks like, and this is the cluster of it. So with this particular arrangement, or with this particular structure of octahedral molecule, we will try to understand Bailer and Ray-Dutt twist. All right. So what I'm going to do is, first of all, I'll show you that this octahedral molecule can basically be converted into a trigonal prismatic structure. So here is one more model of a trigonal prismatic structure. So this is how a trigonal prismatic structure looks like. All right. So you can see over here that you have, this is the trigonal prismatic structure, although this is not that fixed, but yeah, this is your trigonal prismatic. So this particular structure, which is octahedral in shape, this can basically be converted into trigonal prismatic. What I have to do is, I just have to remove these bonds. Basically these are not bonds, okay? If you see, the actual bonds are shown in this particular arrangement, where we have the octahedral and equatorial bond, sorry, the axial and the equatorial bonds, right? So this arrangement was showing us in the octahedral complex, where is axial and where is equatorial bonds. This structure of the cluster shows you just about that where the ligands are, and they are joined with each other through imaginary lines. So all these red lines which you are seeing in this particular image or this particular like model are basically the imaginary lines, right? Now what I can do is I can just remove three of the imaginary lines. Let's say I'm removing one of the imaginary line from here, one of the imaginary line from here, and one more imaginary line if I remove. So this structure is now going to become little bit similar to your trigonal prism, right? So what I have done, I have removed some of the imaginary lines, and now the octahedral structure is converted into your trigonal prismatic. And if you twist it once again a little bit, and if you add these imaginary lines or these bonds, these are actually not bonds, right? So these are all imaginary lines. So if you add these imaginary lines, it get converted back into a octahedral structure. So what does that means? It means कि a octahedral molecule or a octahedral cluster can do twist and can get converted into trigonal prismatic structure. All right, now I'll try to show you that how a twist is performed and how the enantiomers are formed in Bailer and Ray-Dutt twist. So for that I have just modified this particular arrangement a little bit. So let's say we have two of the same type of molecules. Here I have just tried to show these chelating ligands through these temporary arrangements which I have made in the structure. But yeah, this is how it looks, right? So these are two of them. You can see these are both identical right now. These are both identical identical structures. Both of them are same isomers, right? So these are not enantiomers, these are not mirror images, these are both same, because you can see the bonds. This side you have the same type of bond, this is the same type of bond, and this is also the same type of bond. So these are not mirror images of each other. So right now we are having some two structures which are actually same in like arrangement of atoms. So what I'm going to do is I'm just going to perform a Bailer and Ray-Dutt twist in one of the structure, and I'll show you that how that structure will get converted into the enantiomer of the other. So let's keep this green one aside. Let's not do anything with that. Let's perform the Bailer twist on this. So the Bailer twist is performed through this particular phase which is having this C3 axis. So you can see that you can have this C3 axis along this plane, right? You can just pass a C3 axis. If I show you with this pen, so this pen, if I pass it through like this, so this pen is now showing that it has a C3 axis. You can see it can rotate along this pen in a C3 direction like that, right? So you have this C3 axis present in the molecule. So what I will do is I'll just remove three imaginary lines, and I'll try to see that whether I'm going to get the enantiomer or not. So make sure that you are removing it through the face, keeping the face which is having that C3 axis towards you. Okay, I'm holding the downside and I'm just now going to remove three of the imaginary lines. All right, so let's remove them. So once I will remove these lines, so this is going to become something like this. And now see, I have not done anything to it yet, but I can rotate it, I can twist it 60-degree like this. Okay, so this is going to be a transition state, and this is what I have formed. See, this particular transition state is trigonal prismatic, right? And this is going to be the transition state in the Bailer twist. You can see it, it's a trigonal prismatic, right? Now since I have performed this twist in the clockwise direction, I can again do this twist again, keeping the downside fixed. I can rotate it by 60-degree again, and then I will just put back these imaginary lines. All right, so I'm just going to put them back. So this is going to become something like this. Okay, I'll just arrange them a little bit. Fine, so yeah. All right, so this is what my structure is going to look like. Now if you see this, and if I show that what this structure is to this, you can see that now what I have performed after the Bailer twist, this is basically a mirror image of each other. You can place a mirror in between both of them, and both of them have become mirror images of each other. These two are on the opposite sides, these are on the same like opposite face, like mirror images of each other, and this also mirror images of each other. So see, we have just taken one of the enantiomer, we have just taken one of the molecule and we have just performed Bailer twist and we got enantiomer of the other. So these two have now become enantiomer. So we have not broken any bond, okay? There is just a twist which has happened in the molecule, and with the help of that twist we got a enantiomer of that. So this is what Bailer twist is. Now what's that Ray-Dutt twist? Okay, so let's now see what a Ray-Dutt twist is. So I'll not change the molecule, let's keep it like this only. Now we know that both of them are enantiomers of each other. We'll try to perform the Ray-Dutt twist on the same molecule, and we will see that whether we will get the same molecule back again or not, okay, after performing the Ray-Dutt twist. So let's keep it aside, and once again the Ray-Dutt twist says that you don't have to perform it along the C3 axis. The C3 axis, if you remember, this was the C3 axis, right? I have shown you that this was your C3 axis. So let's not do it along the C3 axis. Let's do it along some other face which does not has this C3 axis. This is the face which does not have the C3 axis. Now you can perform the twist here again to check out that whether it is going to give you the same molecule back again, because you are performing it on the enantiomer, so you should get the same molecule back. So again we are just making sure that we are not performing this twist on the face which has C3 axis, okay? Apart from that, we are doing it on some other face which does not have that C3 axis. So now let's try to break 3 of the imaginary lines. So let me just take out 3 of the imaginary lines. So that goes something like this, right? Okay, and yeah, all right. Now I can just rotate this to check it out. So once I rotate this, this is what I have got. See, this is again a trigonal prismatic structure. If I keep it and show you, this is basically a trigonal prismatic. So this is the transition state which you get in the Bailer twist. Okay, so this is what you got in the Bailer twist. Now since I have performed the twist like this, let me do the twist further and put those imaginary lines back. So this is what I am going to get. So in order to check these molecules, what you have to do, just keep them like this. So see, now they are basically identical. You can see them. I just have to move it a little bit to make this thing very clear, right? So these are identical to each other. See, this bond is on the same side, this on the same side, and this on the same side. So what I have done, I have taken two identical molecules. I have performed Bailer twist on this, and we saw that it became enantiomer of this molecule. And when on that enantiomer I performed that Ray-Dutt twist, I got this identical molecule once again. So this is what Bailer and Ray-Dutt twist is. Just on this molecule, you have just seen that how these Bailer and Ray-Dutt twist are going to be performed, and how the structures get formed from one of the enantiomer to the identical molecule. Now we'll talk about the transition state. Okay, that is more important to know, that what happens in the transition state. So let's look upon the transition state. So again, once again, I'll do a Bailer twist on this particular. So this is the C3 axis which I have. So along the C3 axis, Bailer twist is always performed. Okay, so this is the C3 axis which I have in the molecule. So I'm just going to perform Bailer twist. So I just have to remove 3 imaginary lines. So let me do that. So on removing these 3 imaginary lines, I'm going to get this as my transition state. Okay, 1 minute. Yeah, so I am going to get this as my transition state. Now if you see this transition state properly from all the sides, you will see that this transition state has a C3 axis which passes through this. Okay, it has a C3 axis which passes through this particular point. Okay, the C3 axis passes through this. Also you have perpendicular C2 axis which passes through like this. Okay, so you have perpendicular C2 axis also along this. So the point group for this transition state is basically D3H. Okay, it has a horizontal plane of symmetry also. So the point group for this transition state is basically D3H. You can see it from side also. So you can have the C3 axis is going to pass through the molecule from the center like this. Okay, this is the C3 axis, and this is how the C2 axis are going to pass from here. So C2 axis passes like this. This is the sigma h plane. You can see it from all the sides, and you will yourself understand that this basically is having a point group of D3H. All right. So this happens when you perform a Bailer twist. So a Bailer twist on a molecule gives you a D3H point group in the structure. All right. Now the other one, let's try to perform the Bailer twist on this particular molecule. So we don't have to look upon the C3 axis. Let's take some other axis where the C3 axis is not there, some other face. On this face, if I perform this if I perform the Ray-Dutt twist on this, so I just have to remove 3 imaginary lines. So I'll just remove them in order to make the twist possible. And then if I do this twist, so this is basically what I am going to get. Now this particular molecule, if you see, it does not have a C2 axis of symmetry. Okay, it does not have it does not have C3 axis of symmetry, because here you have the bonds like this, and here the bonds are in a different way, right? You can see, but it has a structure of C2V. You can see it in this way. See, this is having a structure of C2V, where these two are like these two chelating rings are going to behave as the two sides, and the axis is going to pass through this. So you can have an axis like this, and you can just rotate the molecule in this way. Okay, so you can just rotate it along the axis passing through the center of these two molecules. Okay, so the axis is going to pass through the center of these two bonds. So this makes this molecule having a point group of C2V. So the transition states in both of them are different. The transition state in the transition state which is there in your Bailer twist has a D3H point group, whereas the transition state which you have in the Ray-Dutt twist, it has C2V point group. So the point group is very important to be noted for both of the transition states, right? Now since you have understood the transition states about your Bailer and Ray-Dutt twist, now the question is that which operates when, or which twist is performed when. Now there is no experimental proof for that, right? But computationally it has been found, computational study is told that when this particular bite, okay, this is called as bite. So that means the distance between the same type of atom of a particular chelating group. Okay, so when this bite is shorter than the distance of this between the two different ligands. Okay, so these are two different ligands. So distance between two different ligands is bigger than the bite. Bite basically means the distance between the same atoms of the chelating ligand, right? So when this bite is shorter than this particular distance, in that case a Bailer twist is performed. And when this bite is bigger than the distance between these two bonds, in that case your Ray-Dutt twist is performed. So this is to be noted, but this is just a computational study which has been done. Probably on this also questions can be asked. So let's now see that what type of questions you can have on this particular topic. All right, Ray-Dutt and Bailer twist. I hope that this whatever we have discussed up till yet in this session is much clear to you, and you guys understood that what this twist is all about. All right, so let's take some of the questions based upon what we have discussed in the video, and I am giving these questions to you guys. Okay, I hope that you all will be able to answer it very easily. The first question over here says that what is the expected point group of the transition state for the Bailer twist? Now I have emphasized on this particular part a lot more in the video, right? So I hope you are quite aware about that. You have four options: D2H, option B C2V, option C is D3H, and option D is C3V. Look upon the options carefully, and if you have missed the topic, just rewind the video, just watch it once again, and tell me what is the correct answer in the comment sections below. Okay, which option is the correct one, and what is the point group of your transition state for the Bailer twist. Let's go for the other question. The other question says that which of the following complexes can show isomerization through Bailer and Ray-Dutt twist? Or the question can be framed in a different way, that which of the following complexes can show isomerization through twisting mechanism. So this Ray-Dutt and Bailer twist are basically twisting mechanisms. So which of the complexes are going to show isomerization with this twisting mechanism? That's what the question is. Your four options are like COEN whole twice Cl2, then you have nickel complex NiCl4, then you have option number C Na2CuEDTA, and option number D is your COEN whole thrice plus 3. En is ethylene diamine, EDTA you all know. So that's what the question is. You have to answer it in the comments below. I am expecting a lot of answers from you because I think you have understood it, right? So that's all for this video, guys, and that's all from my side. I hope the video was informative. You got to know a clear idea about Bailer and Ray-Dutt twist. If you are new to this channel, please subscribe to the channel. If you like this video, give it a like. Thank you so much for watching, and I'll see you in the next one. Until then, have a great day. Bye bye.